Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Philip Massey with us today. Hey, Phil.
Hi. How are you doing, Francis?
I am doing wonderful on this June 11th, 2021. And Phil, where are you located at?
I am at Lowell Observatory in beautiful, warm, but not hot, Flagstaff, Arizona.
Okay, I'll take that as a pickup. So I am in a hot place. I'm down the road from you a little bit, about 2 hours or so. So I'm in Phoenix, and it's quite warm today.
What's your temperature like?
Today we will probably hit on the order of about 37, 38 C. So it's getting toasty. 110F up there around, maybe a little less today, but going well. So you're at Lowell. Is Lowell back to full operation? Not
quite. We've gone to phase 2B, which means that people are welcome to come in and work from their offices, or they're welcome to work from home. We have a very large public program, and the public program is still in the ramping up phase.
Okay.
We don't require masks while people are walking around outside, but we're limiting the tour groups to, I think it's a size of 10 or so. And it's by reservation only to keep the crowds down.
Right.
But it's very, for instance, right now, I think my graduate student is in upstairs, but I don't think, and our director is in his office, but I don't think anyone else is in the building right now.
Cool. I can't help but notice, just, I just love that wood door, right? Because it gives a sense of the history of the place to have a wood door like that.
Exactly. I feel so privileged to work here. On my window, I have this window that's big enough that I need two hands in order to open it.
Oh, excellent.
I have the window open now. It's very pleasant, 75 degrees Fahrenheit out.
Nice.
A little bit of a breeze.
So you don't have a Bluetooth Wi-Fi button that automatically opens your window for you or something?
No. Thank goodness.
Awesome. Phil, what do you like to do for research?
Well, I work on massive stars. I'm primarily an observer. I'm privileged to work with some incredibly fine collaborators, including the evolutionary group in Geneva and Jan Eldridge in Auckland. And then my research group is actually pretty well distributed. Catherine Nugent, who just got her PhD from the University of Washington and is now going to go to the Dunlap Observatory as a Dunlap Fellow in the fall.
Cool.
We've been working together for 10 years. Dr. Emily Levesque at University of Washington. And so we're pretty well distributed and stay in contact by Skype and so on. In some ways, the pandemic had sort of minimal influence on our getting together.
Great. And that is going to bring us to this very lovely AJ article. The Red Supergiant content of M31 and M33. And Phil, take us away.
Well, so I'm going to preface this a little bit by saying that so I get paid for doing what I would do for free. And one of the cool things I get to do is work on massive stars in nearby galaxies. And the way we've rationalized this in proposals is that we don't have to deal with the uncertain distances in our own galaxy. And we don't have to worry about large amounts of reddening and so on. And I get to use big telescopes all around the world. And so it's exactly the sort of thing I love to do. This paper, we've been, I guess I first started worrying about red supergiants in about 1995 or so, maybe even earlier. And I messed around with the content in the Andromeda Galaxy in M33 back in the paper in 1998, where we took spectra of a few stars, but this was our first, what we needed was a complete census of the red supergiant content of these nearby galaxies.
Mhm.
And in a little bit, as we go along, I'll go into the reasons for that. There are three things that are difficult about getting a complete census of any type of stars in nearby galaxies. And one of them is you have to worry about foreground contamination. And you also have to worry about whether or not you're picking out the right kind of objects. And in M31 and M33, the two big difficulties are that there are lots of these annoying little red dwarf stars that other people study for a living, and they're really nearby. But the red supergiants in M31 and M33 have the same color and the same magnitude as stars that are nearby. And so one issue has always been, how do you separate foreground from honest to goodness M31 and M33 stars? And we'll show you how we've done that.
Nice.
And then the second issue has been the AGB star content of these galaxies themselves. How do you separate red supergiants from AGBs? So maybe we can go to one of the figures and
Sure.
I can give you a sense of what we did and why.
Okay. Here's some of the imaging characteristics. And let's go to figure 1. Let's take
Yes. So several years to me, it was actually around the year 2000. So 22 years ago.
Time flies.
Yeah, time flies when you're having fun.
Indeed.
And I do have fun.
Good.
I was the lead on a project called the Local Group Galaxy Survey,
Okay.
where we imaged all of the galaxies in the local group that were currently forming stars using the Kidd Peak 4-meter mosaic camera and the CTIO mosaic cameras. And these green squares, this is of course a picture of the Andromeda Galaxy, M31, and these green squares show you the region that we had done in the LGGS. And to me, this is important because what we're going to do, what we've actually already done, but in the future relative to this paper, is we're trying to study the evolved massive stars. That, as a line that we like to quote in proposals, is that these evolved massive stars act like a magnifying lens, revealing the faults of earlier stages of calculation, errors in the calculations in the evolutionary tracks.
Mhm.
And red supergiants are great. Red supergiants come from stars that are between 8 and say 25 or 30 solar masses.
Okay.
And they have ages between 10 million years and 30 to 40 million years.
Okay.
The other type of massive star that an evolved massive star is a Wolf-Rayet star. And these come from higher mass stars and have younger ages. And these green squares, although we don't discuss that in this paper, these green squares are there as a little reminder to ourselves of what areas had been completely surveyed for Wolf-Rayet stars by Catherine Nugent and myself and others in our group. So when we started worrying about the getting a complete census, it turned out that one of my good friends and colleagues from the days of when I was a postdoc at the DAO, Stefan Croteau, he had a graduate student who had taken images with the CFHT, the Canada, France, and Hawaii telescope on Mauna Kea, 300.6 meter telescope, and this wonderful androids photometry. The complete thesis was never published, and I think that was of some frustration to Stefan. And he was delighted to share his data with us. And so these yellow squares all represent the survey field that they had done. And they had images. We redid the photometry from scratch from these images. But you can see that we now have very good spatial coverage. And this is all taking place in the near infrared and the J and K filters, mainly because we want to, not only are red supergiants red, but we also want to avoid, as much as we can, problems with extinction, interstellar extinction. And a colleague of ours in Greece, Ming Yang, had developed this wonderful technique after decades and decades of people being frustrated by this. How do you separate the red supergiants from AGB stars? The answer is you can do this very simply in a color magnitude diagram of just K versus J minus K, which we'll get to in a moment. So this shows a survey field in M31. And if we skip to the next figure, I believe, we'll see the data for M33.
Mm-hmm.
And again, the green squares represent where we had surveyed in LGGS, which includes the Wolf-Rayet stars. And there were this very wide field survey conducted by Mike Irwin with the Mauna Kea Euclid telescope and the wide field camera. And again, this came by way of J and K. So unusual for us. It was a project where we never actually took our own data.
Okay.
Okay. But I got to do the photometry.
Nice.
So that's something. So let's move ahead a couple of figures. And
where would you like to go?
Well, let's see. Let's skip over the photometric errors as we had talked prior to this. This is a nice figure. So this is a color-coded image on M31 and M31 on the left, M33 on the right, where we show all the photometry, in which we have used, of course, now we have this wonderful power of Gaia. Gaia can't tell us anything about stars in M31 and M33, but it's very good at helping us eliminate the foreground stars. Yes. And on the top row, we see color-coded. The red stars are the ones we expect to be foreground. The black ones, the ones that Gaia has told us absolutely must be members of the galaxy based on them having proper motions and parallaxes that are essentially zero. And the blue points are the points that there are actually no Gaia data available for. And the green ones are the ones we couldn't decide. And I should say that our co-author on this, Maria Drout at the University of Toronto, had done this work for us. And she is the expert, in my opinion, on this. And the bottom figure shows what we expect from the Bezacon models of the Milky Way by way of foreground at these galactic latitude and longitudes. And the agreement between what Gaia tells us are foreground and what the Bezacon models tell us should be foreground, it's just amazing, I think. And so we already get a good clue from these black dots of where the actual red supergiants are. They're not that nice red streak going vertical. Those are just foreground things that we don't care about, mainly yellow dwarfs in the nearby. Okay. So let's move on to the next figure or three. Yes. So here we come to where we've applied what Ming Yang did in a couple of really fine papers published in the APJ and AJ over the last few years. His group is very active in this, and they started with a small Magellanic Cloud, and they demonstrated that you can, in the color magnitude, it helps that I've color coded this, but these black dots, I realize pointing at the screen isn't going to help any, these black dots on the, yes, thank you. Those are mainly the AGB stars. We'll come to a much nicer diagram in a little bit. Those are mostly the AGB stars, and these stars in red are the ones that we have defined as being red supergiants. And these two diagonal green lines show lines of constant bolometric luminosity.
Okay.
So, and we were the bottom one is a log L over L naught of 4, so 10,000 times the luminosity of the sun, which to us is getting to the uninteresting low luminosity stars. And then the second yellow band is for 4.3.
Okay.
This little arrow here shows us what a reddening vector, that's a magnitude of extinction would be. But we don't have to worry about the magnitude of extinction in M31 or M33 because we're working in the near infrared where the extinction in K is only 12% of whatever we have in AV.
Nice.
And what we've found from other studies is the foreground extinction is on the order of, if you look at OB stars towards these galaxies, we're looking at EB minus Vs that are about 1/10. So we're talking about a few tenths. Red supergiants tend to be more heavily reddened than the OB stars because they have circumstellar material around them. And so we wound up adopting for most of the stars in the sample an A sub V of 0.75, which translates to virtually nothing in J minus K and in KS.
Okay.
Let's move along to some other figures.
Okay.
Let's see what we find. So let's skip the table. Nobody really cares about that. But so we had cables. We give our photometry of all the red supergiants in these stars. And they're, I forget what the numbers are, it says in the abstract, but on the order of 7,000 in each of these.
Wow.
And,
that's why they render. Okay, got it.
And one of the, we decided not to publish all of that.
But they are available online.
They are available online and available to anyone. And they include references to the LGGS, which if we know the optical photometry and we know the spectral type, or maybe we've gotten a radial velocity, it's in there.
Cool.
And we also, if we back up to the table for just a moment, one of the fun things we include is this value rho, which is if you were, so you're looking at M33 kind of face on, M31, you're looking at a really unpleasant angle. The rho is the distance, galactocentric distance within the plane of the galaxy. So if you want to know, if you want to look for things like metallicity effects in M33, which has a nice metallicity gradient, M31 doesn't have much of one, but nevertheless, it's kind of nice to have rho in there.
Very good.
So, okay.
Rho here,
Yeah.
Very
and if we go on, so we'll come to, so what happens exactly? So if we, so we use the Mach stellar atmosphere models to convert our J minus K to luminosity and effective temperature. And we compared these to the Geneva single star evolutionary tracks.
Yes.
And we see what, in my mind, is just amazingly superb agreement that where the tracks bend over, so do the temperatures of the points. That there's very good agreement. There are a few high stars that are a little bit more luminous. And I actually, in retrospect, we're currently writing in the current paper, I think we overestimated their luminosities. I think these stars are not heavily reddened stars, the 3 points at the very top in the M31 diagram. I don't think, those points shouldn't be there. And we're fixing that in our next paper, of course.
We'll get a
and then we see in just what I think is a very nice vindication that both the stellar atmosphere models work and the stellar evolutionary models work. So that was nice.
That's nice.
Yeah.
Very cool.
If we go on.
Let me ask while you're on this.
Yeah.
Binarity.
Yes.
Are you sure that all of these are single stars?
Absolutely not. And I Francis, I couldn't have paid you to have asked that question. This is so. Why did we bother to do this? Why did we actually care?
You can pay me if you like.
Well, that's okay. Nobody, so why did we bother to do this paper? And the answer was really the kick in in the bottom for the timing of this paper was that Catherine Nugent had been doing her PhD thesis with Emily Levesque on measuring the binary fraction of red supergiants.
There you go.
And this was something that had never been done. That before Catherine started her thesis work, there were maybe a dozen red supergiant binaries known in the Milky Way and none anywhere else. And what Catherine did in her first paper was show that if you have a binary companion, that companion almost has to be a B star. If you have a B star, if you take a spectrum and that includes the upper Balmer lines, you're going to see it. And she demonstrated this by using model atmospheres and stellar evolutionary tracks. And we had some time on the MMT to take spectra of Wolf-Rayet binaries, unrelated, but there were a lot of spare fibers. And my goodness, a month or two after she had given me the list, we knew about a couple of hundred of red supergiant binaries in nearby galaxies. Very nice. But her goal was to find what the binary fraction was. And if you know where you are in the Magellanic Clouds or in the M31 or M33, and you've explored the number of binaries, you need a number to divide that by to know what the fraction is. And that was why Catherine wanted me to do this paper now and not a year from now. And so we wanted, and another mistake that I think people have traditionally made is they talk about what's the number of red supergiants in the galaxy. The question actually makes no sense to me. That what you want to know is what's the number of red supergiants more luminous than a certain number. And so if you specify that number and say how many red supergiants there are, now you're doing science. And so what we wanted to know was the number of red supergiants as a function of luminosity in both these galaxies. And this led, so her most recent paper in the AppJ on, and maybe this would be a great thing for you to interview her about sometime, shows that the binary fraction of red supergiants depends surprisingly on metallicity. That if you look at the SMC and the LMC and M31 and M33, and within M33, you see this nice gradient in what the binary fraction is. And this is true, after you've corrected for observational bias and the like. And that's a completely unexpected result.
Nice. Okay.
So going back to this paper, since we're talking about this paper, one of the, let's move on to what I think are the final figures in here. Yes. So one little problem, that's an ugly figure, isn't it? One of the problems, one of the annoyances, one of the surprises to us that I struggled with was when we matched the red supergiants detected in the near infrared to the LGGS, which was optical. For M33, we had like 80 to 90% match. No surprise. When we did it for M31, it was more like 50%. And that was very troubling. And oh man, I spent an extra couple of months trying to get to the bottom of this during the photometry. And the answer really had to be reddening. I've always assumed that the reddening in M31 is pretty uniform. And that was based not just on making it up, but on the fact that we had studied OB stars. But I think that the OB associations you see are the ones that are kind of popping out. And sure enough, if we did a map of where, sorry, should have disabled that. You have disappeared.
I have disappeared.
There we go, we're back. Okay, sorry, I went to a different desktop. My apologies. We compared the number of, we made a little map of where we see the highest number of matches and where we see the lowest number of matches
Okay.
between the near-infrared selected sample and the optical selected sample. And it turns out it very well matches the extinction maps that have been made of M31.
Okay.
And so there really isn't much of a mystery. And I will say that when Catherine did her work, what she then did was restricted the sample to where the matches were high.
Okay.
And we're all think we're happy now.
Good.
But that was kind of an interesting result. All right, so let's move on to what I think is So I love these figures, and you know, we all say that the refereeing process is something we appreciate. But I think privately, we would all agree that it's a pain. And then what we want the referee to say is, I loved your paper. There's nothing I would do different. You know, love your work. Everything's great. You guys should publish this immediately. And we had a very kind referee for this paper.
Nice.
And this referee, sorry to put it like this, actually made a good suggestion.
Well,
And that as speaking as a referee, I'm not sure that I've ever made a useful suggestion to anyone. But this referee did. And what the referee said was, okay, so you have these stars, you've separated what you think are the red supergiants from the AGB stars. Why don't you put in a figure that shows what the distributions are like? And it's brilliant, because the AGB stars, they're like, things like the sun that have evolved. And so we're talking about things now that are billions of years. And for the red supergiants, they're a few tens of millions of years. And look how wonderfully different these distributions are. In M30, the spiral arms are well delineated in M33 in the upper right, and over on the left where you were, we see the wonderful CO ring where all of the recent star formation has taken place in M31. And when we look down at the two green ones, we don't see anything like that. They're just uniformly across these galaxies, just as you would hope. And I love these figures. They're my favorite figures from the paper. And we owe it all to this anonymous referee. Sometimes the process works. So if you're listening out there, whoever you were that refereed this paper, thank you. This was a great idea.
Shout out. Very cool. Very cool. We like all authors to say the review process improved their paper. But,
yeah. Well, we all say it, Francis. But we don't say that to our co-authors or our colleagues all the time.
I imagine not.
we do say, well, okay, that wasn't so bad. And sometimes we say, can't they even read?
Yes.
But over time, I hopefully learned that when they say, I didn't understand this, the correct response is not, you should. It's, yeah, okay, I'm going to have to reword that because.
Correct. I wasn't clear enough.
Yeah, I wasn't clear enough. It's really not that big an ambition.
That's right. Very good. So, A+ for Phil.
Well, we'll see. I'm waiting on the referee's report right now. So we'll see if I feel as good about that one. So I think this pretty much.
These really are nice figures. These are nice.
Yeah, yeah. It was a good idea.
So what do you take away from all this? So
what I took away from this are, I think, three things. One of them is, first off, there's a lot of archival data that's useful, right? I mean, I was delighted to be able to make such good use of Stefan and Mike Irwin's data. I mean, this was nice. We used it, in both cases, we used it for a purpose that they didn't intend. The second takeaway is, man, the evolutionary tracks really agree with what, this conversion. And maybe we're off by 100 degrees Kelvin. There could be systematic issues at that level,
Sure.
but that's pretty good.
Yeah.
And the third takeaway, I think, is that there is this method of distinguishing the AGBs from the red supergiants that Ming Yang developed and has worked on really does work. That this was a problem first noted, to my knowledge, the first mention of this was by Wendy Bruish and Jay Gallagher back in the 1980s, in which their recommendation was you just have to ignore anything fainter than, and a bolometric luminosity of 5 or 5.5. Okay. And we don't have to do that anymore. And it's really, we had a referee who made fun of this the first time we used it in the paper and said, oh, you can't tell the difference just by drawing the little lines in the color magnitude diagram. Well, it turns out you can. And those final figures, I think, kind of demonstrates that we're not totally wrong about this.
Cool. Very nice. Very nice. Well, first of all, Phil, I want to thank you very much for walking us through this very lovely AJ article. Thank you. And let me ask you, where does the community go, let's say, over the next 5 years? Should we discover tens of thousands of red supergiants in M31 or 100,000? So are there additional surveys coming? Are there binary models that one might want to apply the data to, et cetera? So just kind of give it a future look on where we go.
Well, I'm going to give you 2 different timescales. One is in the next month, I hope, if the referee responds, and then one that's a little bit further down the road. Okay. So one of my motivations in doing this is that for going back to, I'm going to tell you a short story if we still have time.
I love short stories.
How I got into this game when I was a graduate student and working on massive stars in nearby galaxies was in 1980. There was this paper by Andre Madeira and collaborators who suggested that the relative number of red supergiants to Wolf-Rayet stars was highly metallicity dependent. Okay. And just a beautiful figure that showed this wonderful correlation with metallicity. And when I was privileged to write an annual review paper in the early 2000s, I did the best job I could estimating what the red supergiant content was. We didn't know the Wolf-Rayet content very well, but I thought we kind of knew each thing. You divide them and you draw you put them on a plot of metallicity. And there's this beautiful correlation. And going from lots of red supergiants at low metallicity to very few red supergiants at high metallicity, and yet the models were flat. Despite what Andre said, the models, you could never get the models to agree with this. And we're talking about differences of 2 orders of magnitude. Yeah. And to me, this has always been a big mystery. And Jen Eldridge got very interested in this problem, and he included binaries. Turns out if you include binaries in your evolutionary models, the distributions are still relatively flat, but the data were showing this. So one of my motivations in doing this was I wanted to be able to compare the relative number of red supergiants to Wolf-Rayet stars and do it right, and do it as a function of luminosity. And it turns out that if you do that, the models have been right all along. It was the observation. It turns out if you take an uncertain number and divide it by another uncertain number, you get garbage. And just by coincidence, it happened to look like there was a great metallicity dependence. And so this is where we've gone next. And hopefully the referee will agree with us. And then down the road, I just went to a fascinating session at the AAS meeting. Emily Levesque had organized this wonderful meeting within a meeting on Thorne-Zykov objects.
Yes.
And one of the speakers at that was another of Emily's graduate students, Trevor, and I'm spacing out his last name. Oh, this is horrible. Who gave a very nice talk on machine learning algorithms that can easily be applied to JWST data in order to pick out red supergiants at much greater distances than what we're talking about in the local group. Okay. And the feeling is that in the future, we'll have a much larger sample of red supergiants. And his point being that this will give us a larger sample to see if we can in fact find TZOs among.
Cool. Very nice. Excellent future ahead, both for everyone involved in that. That's great.
Yeah, sorry, Trevor Dylan Wallenstein.
There you go.
Yeah, sorry, Trevor. Shout out.
You gave lots of shout outs. That was fantastic. Phil, I want to thank you so much. And that'll do for this one. Thank you, everyone. And we will see you on the next one. Bye-bye.
Thank you very much.